Okay, so let's see. So I finished updating the slides for last class. Tried to make a bit of the details that we glossed over precise, and so I'm more or less done. So today probably I'll post it. Today we move on to a completely somewhat different topic and different algorithm design principle, which is what we call implicit regularization, because it's trendy, but we'll find out that in fact there is a much older name, and the idea is somewhat classical. Regularization. Okay, so let's see. So far, we essentially built algorithm following one recipe, which was ERM, potentially regularized, so minimizing this. And then GD or SGD. Okay, so some iteration where you do WT plus 1 equal WT minus gamma, maybe gamma T, and then some GT. Okay, where GT is some either is the exact gradient of this, or is the gradient of a term in these sums, or so on and so forth. Okay, but this has been the way we build algorithms. Okay, we mostly focus on linear models and squared norms. Okay, we looked at a few different loss functions instead. We have seen that if you want to go beyond linear models and consider, say, features, then you can simply do this change and the whole thing remains the same. And we have seen that at least if when we are dealing with square norm, there is also another trick we can do, which is essentially replacing, well, let me write it like this, replacing inner product with kernels. Okay? And then, again, we can somewhat play the same trick. So this is what we've been doing so far. This is our bag of tools, bag of tricks to build learning algorithms. We discussed gradient descent. We discussed subgradient descent. Subgradient method. And we discussed stochastic gradient descent, a different way to perform this depending on the smoothness of the function or how exactly we want to deal with this gradient. Okay. In all situations, if you remember the very first, one of the first class when we discussed least squares, the idea was if the problem is nice or the model is not super complicated, then we don't need this. We just don't need it. Okay, we can just solve things directly. We introduce things like the minimal norm solution of our least squares and just the least square solution, for example. You can do the same thing. You put lambda here equal to 0. But we discussed that perhaps we need a way to, if you have many possible solutions, to select one, for example, the minimal norm solution, okay, according to some norm. And maybe if the data have some instability, you do need to add some lambda, okay? And we did this in a couple of different ways. We took the point of view of minimal norm solution for least square, discussing the connection between numerics and generalization. And then we took more the point of view of classification, where we saw that minimal norm is related to maximum margin. Okay, so that whole discussion, if you remember a bit, was about shall we use lambda or not, and when to use lambda. But the idea was if there's something bad can happen in terms of stability, we can cure it by lambda. That was the basic idea. Make sense? And of course, instead of curing it by lambda, you could cure it by adding a constraint on the W. Okay, so I will talk about constraints or penalization somewhat interchangeably. And the idea is that, again, let me do it just right there. The idea is that instead of doing this, you might do instead something like this. And then the role of lambda is played by R is the same. So, either by constraining or either by lambda, we change the objective, the empirical objective, and do something else. Okay? Now, in practice, it turns out that oftentimes, even if you turn r to infinity, or if you want lambda to 0, you see the signs of regularization, even though you're not imposing any kind of regularization. Okay? Especially in neural networks these days, people have done experiments where they basically run an experiment, okay, get some results, and then turn off all the switches that they think of as regularization. Weight constraints, okay, dropout, okay, or any other trick, okay? You just turn it off. And nothing. You get the same result, or almost the same result, okay? And then all of a sudden there is seemingly a puzzle, right? How is it possible that you don't overfit even though you turn off all the switches that prevent overfitting? Okay, one solution is the problem is easy. You just didn't need to regularize in the first place, okay? But the situation is maybe there is something else at work that we have just not thought about. And today we want to look at this other option. And we introduced a way to control the stability and control the complexity, growing the complexity of your model, other than penalization, okay? So we do it again in our simple setting. Later on, when for sure Tommy, possibly Sasha, they're going to discuss neural networks, this topic is going to come back, because these days, this is the main way through understanding why neural networks seems to generalize, okay? That's really been a major, say, intuition and perspective on how to understand the properties of neural networks. As we've done in the before, we're going to use least squares at our working playground to try to get more explicit computations, okay? And so here, on the one hand, we have what we call W dagger. Okay, remind me that I have to use star, which is this, okay? And we can view this as the limit as lambda going to 0 of okay, and we've seen that we can write this in a couple of different ways. It doesn't matter. This is just a sketch of what we've done. Okay, and this we should write a star, which means transpose if you're watching from YouTube. Okay, so far so good. Okay, now we want to look at something different, which is this. Consider simply this iteration. Okay. What is this? Simply gradient descent of what? If you look at just least squares and take the gradient from the two, you get exactly that. Okay, so that's the gradient descent of least squares. With no penalty, no regularization. Okay? Well, spoiler, this is going to be the same as this. This thing here, you're going to think, hopefully in half an hour, as you think about this. Okay? Presumably, most of you don't usually. Okay? And they don't, not because this is complicated, just because you tend not to know this. Okay? So we're going to make a couple of deep observations. The first one is that the limit of lambda going to 0, this is equal to this. Okay? So one first way to recognize that this is somewhat similar to, so that this, let's call it the gradient descent, okay? One first way to, I just said, this is the same as that. Gradient descent is the same as Tikhonov, okay? Well, one first way to make sense of what I just said is to prove that he has the same properties in some sense. Okay? So one first property is the one that's written here. This guy, for lambda going to 0, goes to the minimum Norm solution. What about this? Well, we have to agree who's lambda. Because if I say that he has similar, there has to be a lambda. I didn't write it. There is no lambda. Okay? There is something else that plays the role of lambda. Who is it? Well, let's see. We have two parameters here. Where are they? This, and what else? The number of iterations. Okay? Turns out that, so it's not the combination of them, but let's assume for the sake of simplicity that we just put gamma so that this converges. Okay? So we take it out. We just read from the books how to pick it up in order to make it converge. So the only free parameter is t. If you let, so that's the candidate, okay? The candidate lambda is t. Let's convince ourselves that indeed it goes to the right place, which is W dagger. So we want to convince ourselves, it's not going to be quite a proof, but almost, that if t goes to infinity, gradient descent, even though I didn't tell him that I want to go to the minimum Norm solution, or seemingly I didn't do, he actually knows it, and he goes there. Okay? I'm presenting, everything that looks like a paradox is a paradox because you don't understand it well. Okay? But I think this is a common misintuition. Like, how does this guy know that he has to go to the minimum? How does he do it? Why does he go to the minimum Norm solution? It's not completely obvious the first time you see it. You agree? So why does he do it? It's actually very simple. This is going to converge to what? To a minimizer of this. Okay? Which one? Let's assume, just for the sake of simplicity, that I start from 0, because that's kind of the statement I want to make. And you'll see in a minute how much weaker we can make the assumption. If you start from 0, then every time you produce a WT, it's where? It's put 0 here, okay? Then it means that W1 is going to be in the span, or in the range of this matrix. You agree? And then because W1 is in the range of this matrix, if you do go from W1 to W2, it's also in the range of this matrix. So what I'm trying to say is that for all t, with this initialization, Wt belongs to the range of x star. Agreed? In other words, if I start from 0, every iteration lives in the span, is a linear combination of the input points. You agree? So if it converges, and it does, because we fix the iteration so that it converges, it has to converge in this space. It cannot go outside, okay? Well, but remember that W dagger is the unique solution in the range of that, okay? Or in other words, if you want, this is also the orthogonal to the null space. So there's not much more to say about this. So again, let's recap the reasoning. We do gradient descent, okay? We let it run. Where does it go? If I fix the parameters so that it converges, it has to converge to a solution of least squares. If I have multiples, if there is one, you converge to the one and you don't have to ask anything. If there are multiple ones, to which one does it converge to? Well, let's see. Every iteration belongs to the range of the data, is a linear combination of the data. So if it converges, it converges to something, the linear combination in the data. Okay? But it so happens that this was the definition of the pseudo-inverse, was the unique least square solution which lives in the span of your data. So put the two things together, I created an iteration that converges to a solution of least squares and converges to the solution which is the linear span of the data. Turns out that there is only one solution and is exactly the minimal Norm solution.
That's assuming that you have the initial condition.
Right. For now, yes. And once I'm sure that everybody's on board, you or anybody can tell me how much more general you can make that assumption. Is the null space of the matrix. You know, there is the range and the null space, the set of vectors that are turned into zeros. Because it's a fact. If you have a matrix and you look at the null space of the matrix, this is the same as the range of the transpose of the matrix. It's just a basic linear algebra effect. Okay. You remember you can always split, if you have a matrix which is rectangular, you can always split the space in this direct sum of this. Okay. So this and the range of the this guy, the x hat, and this is just an equality. Okay, it's just we are giving that for granted. It's a basic fact. Yeah. Is that okay? So I create too much anticipation because mathematically it's actually so easy to prove it that it's not so interesting, okay? Gradient descent converges to the minimum North solution. Why? Because it converges and because it is always in the linear span of the data, and the minimum North solution is the only one in the linear span of the data, period, okay? So it's actually a remarkably simple fact. If I start from 0, this is true. Which other initialization I can pick and still have these results being true? What was the key point? Pick anything in the range of x. If you are in the range of x, you stay in the range of x. What happens if you're not in the range of x? Say it again?
If you are not in the range of x, then again we converge to
There is going to be a shift, because think what's going to happen. If you start from something which is not in the range of x, because the gradient is always in the range of x, the direction which is not in the range of x is not going to be modified anymore. Okay? So you pick an initialization which has a part in the range of x, but a part outside. The part outside is never going to be modified, because the gradient always lives in the range. Okay? So there's going to be somewhat a shift. You don't converge to this. You converge to this plus a shift, which is exactly the direction outside of the range, okay? But that's not the situation we want to look at too much right now. I mean, this is going to be important in general if you look at more complicated model. But maybe what we want to make is this very simple observation, which is gradient descent converges to the minimum North solution. And so this is the first, that was a hand. This is the first observation where which lambda and not quite t, so in some sense, this is the first clue. What I'm trying to say is that this is the first clue that maybe I can think of, let's say, t as 1 over lambda, okay? So not quite proportional, but lambda going to 0 seemingly does something like t, for Tikhonov, does what t going to infinity does for a gradient descent. Yes? Well, so we discussed quite a bit in details in class 2. There are a few ways of saying this. The one I remember right now how to say it is, because you're taking a minimal North solution, that minimal North solution is unique, okay? That's observation 1. Observation 2 is that when you take the gradient, it has to be in the range, okay? So if the unique is unique and it is in the range. So I think you can do it by linear algebra, and I think it would be a better answer, and I don't remember it right now, okay? But one more indirect way, which maybe is not great, is minimal norm is unique because it's a strongly convex problem, and then because it's the least square solution, it is in the range. And so that's a bit more indirect, but that's, at least it gives you a feeling that that's true, okay? So, and again, it's a good point to refresh why this is true, because that's the only thing we use, this other characterization of the minimum norm. Given that, we're done.
Isn't this another way of saying something about the representative theorem? Like, it's always
Yeah, although at this, absolutely yes. So the remark is, this was the representer theorem, right? Is that thing that says yes. It's just that at this point, we use the representer theorem as a tool to give a different representation of the solution and go from, say, complexity driven by D to complexity driven by N, or to go from features to kernels. Here, we use the same fact, but for a completely different reason. We want to know that we go to the minimum Norm solution. And here, D, N, kernels or not play no role at this point. But you agree, you're right, this is the same Okay? So we sink it in. Gradient descent for t going to infinity goes in the same place as lambda going to 0. Okay? So in a sense, you can call this an implicit, something implicit, okay? Here, we had to add a regularization. Let's put it back in this form. We had to add the penalty to achieve this result, so we do it explicitly. Here is, in some sense, the dynamic of the gradient descent that, navigate the space of all possible solution, hitting the same place where this would hit, or lambda going to 0. So in this sense, it is implicit. Now, we can agree whether we want to call this an implicit bias or a regularization, okay? Probably more appropriate is call it an implicit bias. Why a bias? Because it basically says that gradient descent doesn't like all least square solution in the same way. It likes the minimum norm solution better, and it goes there, okay? So it has a bias towards solution with small norms. And it's implicit because you kind of have to read it out, okay? And notice that the thing, again, at this point, might almost seem but I don't know if you are bored or surprised at this point. But you could, for example, ask, what about another norm, okay? What about if I want to go to another norm? Well, you have to change something, right? Because this guy, this gradient descent for this model, likes the Euclidean norm. It's hidden somewhere, okay? Does he go to the minimal L1 norm? No, he goes to the minimal L2 norm. That's what he does, okay? So in that sense, it has a very specific bias hidden in it.
Sorry, so just a quick confirmation. Does this mean that whenever we have like least square with ridge regression,
and you do gradient descent?
then it's useless to put the...
Right, yeah. So that's, yeah, so the question is, if I do, to be sure that I understand the question, suppose that you do that, but you don't solve it this way, you solve it with gradient descent. Does it mean that you're doing ridge regression and ridge regression? Yes. Does it mean that if you don't do enough iteration, supposedly, this is going to be like putting a very big lambda? So does it mean that in some sense I have two knobs that do the same thing and I have to be careful? Well, we didn't quite prove the whole thing, but it seems like, right? Because in some sense, if this is true, and this is just the first indication, I'm going to give you another one which is going to be even stronger, it seems that I might be doing the same thing twice. So if I don't optimize enough, this suggests that I might be already regularizing, okay? Yeah, but I would say while we're going to discuss things where I know that there are proofs and I'm going to go in more details, I think this is going to be a pretty general fact. There are going to be a lot of situations where you go to different models, nonlinear, neural networks, momentum, stochastic, mini-batch, reshuffling, crazy stuff. And I think this is a pretty general fact. We only have proofs for so many cases, okay? So optimization has an implicit bias inside, and so if you don't remember that, you're essentially constraining your problem twice, once explicitly and once implicitly, okay? And that's why I don't only call about a trick, I view it as a design principle for algorithms, because it's really, it's a new story, right? It's not just, it's something else. Okay? So, there is the usual terminology gap between calling this regularization or not, okay? Again, you can call regularization something like this, in which case this is doing regularization. It's a way to compute the pseudo-inverse iteratively, okay? But you can also call regularization, we call regularization, let me go back to this notation, this. The idea being that there is some instability and we want to cure it, okay? So while at this point it should be clear that this is doing the same as this when t goes to infinity, it's not quite clear if in the process as we go from small t to large t, we generate a path of solution which is the same as the one generated by this. Okay? This says these two things, at the very end, they go in the same place. But if you want another question, let me put it in quotes, is it also true that in some specific sense, not only for, where we have seen that when t goes to infinity and lambda goes to 0, they're kind of going in the same place. What about if t doesn't go into infinity and lambda is not quite 0? Is there still true that they're somewhat behaving similarly? It's not completely clear, right? I mean, from what we said so far, it's not completely clear. Okay? It would be nice, because at that point, really, it means that we can kill lambda. We can just run the iteration as we increase. If you think of lambda as controlling the complexity of the solution, now you would have that is the number of iterations that controls the complexity of the solution. Opposite to lambda is when the number of iterations goes to infinity, that potentially you go and explore a larger space, if needed. Okay? Because if not needed, you just converge to the minimal North solution. So that's why you have this inverse behavior. Okay? So we don't quite prove. We're gonna try to put some evidence that this is the case. Okay. The first evidence is drawings. So just an intuition. I'm gonna do a Python notebook on the board by writing it. Okay. And bear with me, you agree that if I want to change these and use features, nonlinear features, I can do it calling x phi of x, okay? So I'm gonna do a nonlinear function. So imagine that you have these points, okay? Something like this. Well, maybe let's do it like this. This is x and this is y. So, roughly speaking, it seems like, maybe something like this could be a good idea. I can also go and pass each point, but there might be noise or not. That's the basic intuition, okay? Let's make it more extreme. Let's put a point here and a point here, okay? There is some faraway points, okay? You agree that's kind of what you expect the minimal North solution would do, maybe, okay? Okay, but what's the idea here? Run gradient descent starts from 0 because it's simple, and you get a bad solution. It doesn't fit the data well, okay? Then you keep on going, and you fit the data better and better. So you start from this. Then you're going to pull it up a bit, pull it up a bit. You start to guess the shape. At some point, you get to this. Then what's going to happen is that in a situation like this, you really want to interpolate. Okay? You really want to pass to every single point. So if you have a model which is powerful enough, at some point, it's going to do this. Oh, sorry. It's going to do like this. Okay? Through all of them. That's what the minimal North solution actually would do. It interpolates and it tries to find. So it doesn't go like this. It doesn't oscillate crazily among them, but it still go and pass through all of them. Now, this might be or not a good idea, depending on the signal to noise ratio. Unclear, right? But the good news is that from that intuition, so what are these different curves? Well, I don't know. This could be, say, W0. Now I'm guessing, right? It could be W5, W10, and then at some point this is W large. Okay. What I mean is that you run the iteration, and the algorithm does what it told him to do: fit. Okay. We discovered that it doesn't just fit. It try to find the best simple model that fit the data implicitly, but it's going to make this model more complicated as needed, and at some point it's going to converge. So if convergence is fine, you just let it go. What do you do if convergence is not fine? For example, among those solutions, which one you want? This one or this one? Well, let's say that you want the second one. Intuitively, I try my best to do the drawing so that this is the right answer, okay? How do you do that? How do you get it out of the algorithm? Do you constrain? No, what do you do? Altogether, we say we stop, right? That's what you do. That's what you want to do, okay? Do you have to do it? No. If converging is the good idea, just converge. But now you have an extra knob. It's an extra thing that says, again, it really does feel like t is 1 over lambda from this drawing, okay? When lambda is small, I fit. When lambda is big, I fit less, okay? And in the process, I do a trade-off through simple and complicated. T seems to be doing the same thing. So if as you can imagine, coding this up takes more or less the same amount of time as drawing it, especially if you're my drawing skills. So this is one way to convince yourself, okay? And it turns out that if you look at the old literature on neural networks, this is a trick from the 80s, maybe even before, okay? When you train a neural, it's tempting. You train a neural networks rather than deciding how to stop based on some crazy theorems in convex optimization or non-convex optimization, God knows, anyway, they don't hold. What do? Well, you let it go and you check if the test error, not the training, okay? So you check the number of iterations here, you check the training error, which is gonna go down, okay? Possibly very close to 0, and then you check the test error. And the test error you can expect essentially to have 2-3 behaviors, okay? If the data set, well, let's go from classical statistics to big scale machine learning, okay? If the data is not too high dimensional, okay, and really you might have big noise, okay, so enough points, not so many dimensions, the pseudo inverse is typically a bad idea. Okay, and so what you see is that you see one of these very U-shaped peaked curve. Okay, again, typically you observe this when the noise is sufficiently large, and in some sense you're in a low-dimensional regime. Okay, already if the noise is not so large, you don't expect to have this crazy instability. What you expect to have is more something like a plateauish like situation. Again, this is clear. This is training. This is test. Okay? And again, the way you should think about this is you already learned this calling T 1 over lambda, okay? You just have to map that part of your brain, this new one. It's the same stuff. I'm not spending time on it because we already discussed. Now, if you have not only a situational analytics, but also big data sets, what might happen is that you kind of don't get to that level of precision ever, okay? So you might be in this situation, you might be in this situation, but you oftentimes are just, that's all you can see. So the training error goes down and the test error goes down, okay? And that's what happens, okay? They keep on somewhat, going down together. That doesn't depend on the algorithm, it depends on the data, okay? It depends on how the data look like, and well, it depends on the algorithm in the measure in which it also depends on how highly parameterized is your model with respect to the data, okay? But fixed the data at once, then it depends on, fix the algorithm, then it only gonna depend on how the data look like, yes.
What you're saying is that the noise is high enough, then the neural solution is not.
Yeah, and I'm just, yeah, so what he's saying is, I'm saying that if the noise is big enough, the minimal North solution might not be a good one. And I'm not quite saying it, I'm re-saying it, because we spent an entire lecture saying this. We said when there is an eigenvalue which is small enough, what does it mean small enough? Well, in some sense, you have to be small with respect to the noise, or other way, the noise is big with respect to the small eigenvalue, so that when you divide, it amplifies. So yes, I'm saying exactly that. I'm saying that I absolutely don't want to do it. That's the whole thing. The conclusion is you can put lambda, or what I'm saying here, you can just run gradient descent and stop. Okay? And now we want to make this even more, into the face. Any questions? Yeah.
Earlier when you say that you build the algorithm with lambda and then you turn this knob off and so that you don't need to regularization, you still have low generalization error. But now what you've proven is that without regularization and for this gradient descent to be converted to the same minimization, but what you didn't prove is that with regularization versus gradient, and this penalization error is because
Is the same? Oh, so yeah, I didn't prove anything. I just hand-waved a couple of arguments that suggest that they might be.
But didn't we say that it's good to have a little bit of the regularization term so that you wouldn't have too much of the overfitting?
Sure, and now I'm telling you, so what she's saying is, if I understand correctly, the comment is, we said that this was, so let me be annoying. I said that this was a way to avoid overfitting.
Yeah.
And I'm telling you now that this is another way.
But you just proved this is the conversion to the case when lambda equal to 0.
Absolutely. That's what we discussed so far. Okay, that's what we discussed so far. So here I just proved that they go in the same place in the end. And now I want to ask, do they also somewhat behave similarly, not at convergence, but before? And I did this is the first argument that says maybe they do. Now we try not to quite prove it, but try to further reinforce the idea that you know, what you say it's missing, we try to fill the gap, okay? We want to show that this algorithm here is actually very similar to this expression here, and T is going to play the same role. So that's what we do now, okay? And we're still not going to prove any generalization bounds or anything. We just prove, because it's simple, that this actually looks like this in a precise sense. Okay? Yeah?
With the gradient descent, if we don't want to overfit, we have to stop at some point. How can we make this systematic?
How to stop?
Yes.
Right. So the question for everybody is, if you want to avoid overfitting, you have to decide where to stop. How would you do it? A good chorus would be great at this point.
I mean, you can stop at the right.
What's right? Well, the answer is the same way you choose lambda. How do you choose lambda? And again, remember that whenever we say this all together, it's not because it's great. It's because we have nothing else, pretty much, okay? We have that, and I ran out of time. You know, I asked Tommy, and he has the right answer because he ran, you know, what is it called these days? Gradient student descent, when you have a bunch of students turning knobs for a sufficient amount of time that you know the right answer is 0.213, okay? That's the other option. I think cross-validation as gradient student descent are the most fashionable way to tune parameters these days. You run it for days and days and days, and you try. So there is no magic here. The only magic is that I show you that T is 1 over lambda, almost, okay? Now we want to do the end. So the term early stopping is a bit confusing because it seems to suggest how to stop. It doesn't. It just tells you that stopping does something, okay? It's not a way to stop, but just the idea that you can do it. Okay, let's do the, any other questions? Let's do the magic makeup of gradient descent. So it's based on one calculation and one observation, okay? The calculation is this. Remind me to write stars, assuming that we have anybody hiding somewhere. Then I do not the smartest thing on the world, which is just that I put all the stuff with WT together. So I get identity minus gamma okay? And I do this only because now the more interesting thing is that if you can prove by induction, that is the proof that you use 5 billion times at this point, that this is actually equal to starting again from 0, which I do only because it's simple. This is the same as this. So let me skip the proof of this because it's already a bit late and there's nothing interesting. So the way you do the proof is that you check the base case and then you just plug this expression for t minus 1 in here and you prove that it actually moves on to t plus 1, okay? So again, you use this for t minus 1, you plug it in here and you show that it goes through. So the interesting bit is what that means, not how you prove it, okay? What does it mean? What does it look like? Let's see. Let's do the embarrassing geometric series model moment, okay? Maybe I can even do it without reading it, but considering my latest performance, I'll read it. I think it's fine. So the idea is that in that sum, or what we want to see is a geometric series, okay? So if you take a bunch of numbers and you sum them up, if you take a number a, okay, smaller than 1 and bigger than 0, and you take power, what do you get? You get 1 minus a to the minus 1, okay? If you take 1 minus b to the j, you get b to the minus 1. Okay? Assume that you actually take a matrix A, which is invertible. Okay? So now take, instead of A, take a matrix A invertible. Let's say a nice matrix, symmetric, positive, definite, invertible. Okay? We don't care how general this result is. Turns out that now you can, and you also need the, guess what? You need the norm to be smaller than 1. Then this result hold. You basically replace the numbers with matrices. Okay? Okay, this is not something we can, it's a fact, okay? You can kind of prove it easily if you do the diagonalization of the matrix. This is what is called the geometric series for matrices is called the Neumann series, okay? So this thing that you do with numbers, you can do with matrices as long as the matrices are nice, invertible with the norm bounded by 1, okay? Do you see why I'm pulling this up? Look at this. Yes. The question is what's the norm here, and let's say it's the operator norm. Right, so you can make this more precise, okay, and show that it converts to the pseudo-inverse. Let's assume for a minute that this matrix is invertible, just because it makes the point and it's simpler. So let's assume that n is larger than d, okay, just because. Then if t goes to infinity, this thing goes to x1 plus x to the minus 1. Okay? This is not particularly exciting. We knew it already, right? We kind of knew that when t was going to infinity, it would converge to the minimal norm solution, and we just found it again. Okay? Now, I need this guy, so I'm just going to write it. For the geometric series, we can also write what happens if rather than summing up all the, that's not what we're doing here though. We're not summing up all the terms, we're stopping it. We're stopping after t steps, okay? And this means that we're not taking this, this is not an infinite series, but it actually is a finite sum. So you can now write down what is the finite sum value. Okay? And again, if this was numbers, this would be 1b j equal, it should be it should be 1 minus 1 minus b t b to the minus 1. Okay? So this is just the finite summation of finitely many power of 1 minus b, and the exact kind of extension hold than before. Okay? If you let, so this for finite b is going to look like 1 minus identity minus gamma b to the t b to the minus 1. Sorry, I should write the right matrices. Okay. Okay? And notice that, okay, so I just did the symbol matching right now, okay? So we didn't draw any conclusion. Notice still from the symbol matching that there should be a gamma in front of this, but there should be a 1 over gamma. There should be a gamma in front of this, 1 over gamma, but it was a gamma here, so they go away. Okay, so that's actually the right expression. So what happened, for example, when t is equal to 1? When t is equal to 1, this goes away. You get identity minus identity. Okay, and then you got minus gamma hitting the same thing. So you essentially got gamma identity, which is very much what you get here when you get a very large lambda. For a very large lambda, you're just basically inverting an identity, and you're just using this. Okay? It's the same thing here. So now these start to be, again, it's not a proof, but it starts to be mounting evidence. Okay? They go in the same place. They go in the same place with something that is kind of the same form. Okay? And if I stop, in this case, to 1 iteration, they both approximate the identity. Okay? Now, I would say this again. This is not proving generalization bounds or anything, but at this point, I don't know. I hope you're comfortable enough to start to see the analogy. Okay? Is that okay? So for least squares, you can also do a little more. You remember that we use this, the SVD of the data matrix to get a better handle on the expression. Okay. So here we want to make a few remarks, I guess. Well, let me first do this. So one remark is that we can again rewrite things emphasizing the similarity between these two if we consider the spectral decomposition of the matrix. This is the SVD of the matrix, and this is equivalent to when you apply to a vector to do the singular values. That's the same thing, okay? Here I make it act on a vector, and here here there's some, here I just write the expression in matrix form, and here just the right thing through the action on a vector, okay? Now, this R is the range, is the smallest between n and d, or if they're linearly independent, is the smallest number of independent rows columns. What is the pseudo inverse? I put here y because it's our candidate guy to put there. The pseudo inverse is just uj transpose. Sorry. Sorry, I did it the wrong way. I had to put the vector of the right dimension, and I swapped them, and now you see it. Okay. It's easy to write the pseudo inverse in SVD form because you just take 1 over. Okay. What about this? That's also easy to write because basically all you need to do You just have to tell me what to do to the eigenvalues. And what do? You do an fj of, sorry, an f lambda of sg of any vector s, which is s divided s squared plus lambda n. So again, when you take Tikhonov and you write it in the SVD, you have to say what to do to the eigenvalues. And what you do is that you add lambda n and then you invert. Okay? This extra s comes from the presence of this X transpose here. Okay, so this is W dagger. This is W lambda. What if you do W lambda T? Well, this is gamma J1 T minus 1, identity minus gamma. Which is also going to be the same as this. But now I have an ft of s, which is equal to okay, what's written here is ft of s is just equal to, I guess maybe I should do it like this, what I wrote here. Okay, it's the same expression. It's just that now what I did is that I put it on the singular values. Now, if you think of these properties of the truncated sum, you can view these two things as some form of filtering, where you do what you don't like are not high frequencies but small eigenvalues. Okay? So in filtering, typically say in the classical filtering, one way to do linear filtering is low pass filtering. You like slow frequencies, but you don't like high frequencies because they're related to instability and so on. Here there is an analogy. You call slow frequencies the large singular values, and you call high frequencies the small singular values. And what this does is that the first filter simply say, if you're 0, I kill you. Okay? The second one says, if you're small, I depress you. Okay? Through lambda. The third one, which is a bit, more contrived maybe to check, is I do the same thing as this, because basically I'm taking powers. And so if the S is large, it's not going to be affected too much. But if S is small, I'm really going to make it super small and de facto kill it. Okay? So in some sense, these two ways are ways to filter things in a smoother way. And the larger is lambda, or the smaller is t, and the more you're filtering. When lambda goes to 0 or t goes to infinity, you just go back and don't filter anything apart from what is 0. Okay? So you go back to the pseudo inverse. Is this. I just, why this formula? Well, actually I have it here. It's just spectral calculus. So the nice thing about working with SVD and eigen decomposition is that you can write matrix computation as operation on the real numbers, eigenvalues and singular values. That's what we did here. So what I did here is the same thing that I did here, just I was lazy and I didn't rewrite this expression. I only wrote the difference. Okay? So it's the same thing. You just plug it in and you check that that's true. What time is it? I don't understand. Okay. Okay? All right. So I'll summarize, and in the meantime, you let me know if there is any mistake or questions that we can address. So the whole story started with, so far, we use gradient descent as an optimization technique to solve an empirical risk minimization problem. So in a way, all the modeling aspect of our algorithm design was in the ERM. Okay, that's where we do all our overfitting, non-overfitting. I'm a statistician, I'm a signal processing guy, you call it whatever you want, but you're not the numeric person, right? So we we put on our statistician, inverse problem, signal processing, you name it, hat here. Then we throw it away, and we schizophrenically become an optimization guy, okay? And we look at this. And the two things are really like two moments in time. It's kind of a divide and impera kind of approach. You take two problems and you make it simple, okay? And then what did we do here? We just said, you know what? I'm going to do one thing. I don't do two things. I do one thing. I do this, okay? And a priori, it seems that you cannot do, two pigeons with one stone. But kind of what we try to argue here is that you can, okay? Because at least in this case, this iteration doesn't just go to a solution, but it has a bias towards minimum norm solution. But more than that, it builds a path of solution progressing with t that is very much reminding of the path you get as lambda goes from big to 0, okay? And this, again, is not exactly a proof, but it's start of generalization, but it emphasized the analogy, okay? So we gave the asymptotic perspective. Did I delete it? We had the hand-wavy Python notebook drawing perspective, and then we have this linear algebra perspective. And we can take this more power series point of view or this filtering point of view, okay? Which I like because, again, it drew yet another connection between, say, statistical reasoning and not just numerics, but filtering, which arguably is another big columns of dealing with data, okay? Questions? Yep. There is, so the question if there is a one-to-one mapping within lambda and t, and the answer is kind of yes. There are some you can do like a first order expansion of this f function, which are just one-dimensional. So you can just do a Taylor expansion, I get the feeling. You can do a more refined argument that shows that in some sense that you can make a more refined argument that makes it even a bit more stronger, okay? Yeah. Yes.
What you can do is you can replace a filter that's defined in terms of lambda with a filter that's defined in terms of t.
Absolutely. Right. So yes. So the remark is, with this filtering perspective, you could refine a filter defined by lambda with another filter defined by t, okay? Which doesn't have the same shape, is now defined by different numbers, but that's roughly doing the same thing. This comment kind of begs a question. Why do you want to do it? Why would you do it, right? Why, if you have a nice filter with lambda, go all the way to the end, okay? We discovered a bunch of stuff in the middle, but if the end is that you replace a filter where you call a thing lambda with another filter where lambda is now called t, if you got the story up to this point, that doesn't sound like a great idea, okay? There are a bunch of arguments, I tell you two, okay? One is, well, no way in hell I'm gonna compute the solution like this or like this. Because if I do it like this, I have to compute an SVD, which typically is the one thing that you don't want to do, okay? SVD is the most important theorem in data science, according to Jill Strang, and I totally agree. But it's also definitely one thing that you want to use very carefully when you actually to solve actual problem, because we still are, we can solve a 5 gazillion layers recurrent neural network well, but an SVD on 3 million points, maybe even just 1 million, is a problem, okay? So an SVD is a tricky thing. It takes forever, so you don't want to do this, okay? You don't want to do this either, because do you want to take power of matrices? You don't want to do it, okay? What you want to do is to run this, because it's cheap. How much is it iteration? You have to do a matrix, vector multiplication a couple of times, and that's it. So in that case is ND. And how many times you have to do it? T. Okay, now there is some news that is kind of interesting. If you have to solve this, okay, or if you wish, this, how many iterations you have to do? So you do ERM because you like lambda, okay? You don't like the SVD because it takes forever. Use an iterative solver, and you run an iterative solver on this problem. In other words, you don't work directly with this expression. You go back to the variational formulation, you run gradient descent. So we are back to lambda, okay? Okay, how many iterations you do? You kind of have to go to convergence, right? You have to go to precision, okay? And lambda, how do you choose it? Well, I don't know. If you agree on cross-validation or something like that, you not only have to do one iteration, you have to do many iterations, one per lambda, okay? So the rough cost is going to be, say, solving this by GD is going to be, the cost of an iteration is also NP. T infinity, what I mean here is large T up to convergence, and then you have to do this for the number of lambda you do. Okay? And here, lambda is gone. This is a good way to think what it does, but this is the good way to think what you want to do in practice. And this costs N, P, D, sorry, whatever, let's use D. N, D, T. Lambda is gone, and infinity is gone. You just run as many iterations as needed. If needed is a lot, you go there, but at least you do it once. If it's not needed, because there is some overfitting problem, you stop before. And so, the idea of doing statistics and optimization somewhat now conflate. It just start to be overlapping, okay? You typically think of lambda as controlling the complexity. Now, after this story, hopefully, if somebody comes to you and says, you know that I think of iterations as controlling the complexity of the model, sure, why not? That's kind of the whole story. And now the amount, typically, the way you think about the complexity when you're doing numerics is just based on thinking about this iteration to solve this problem. So you just look at how big is the data, okay? That's what matters. But if you look at this perspective here, where T, let me write it as 1 over lambda. Now, the amount of computational resources you allocate for a problem doesn't just depend on how big is your data, but how good is your data, or how hard is your problem, in other words, okay? If your problem is very complicated, okay, you might need to run for more iterations. If your problem is very easy, you might be able to stop before, okay? If the noise is very high, you don't want to run for many iterations, okay? When I say easy, I mean the objective, the true function. If the true function is complicated, you have to sweat more to get it. If it's simple, you might stop before. If the noise is very high, you might have to stop sooner because with respect to the data you have, you cannot get a very precise solution, okay? So one reason to do all this is to somewhat have this connection between, say, computational actor and statistical aspects, okay? And from a practitioner point of view, this is very natural. You have 15 knobs, and you try to see which one you can just turn off and not use, and just pick the one that you have to use anyway. And iteration is one of those, okay? This question, yep.
So it makes sense from the point of view of easy in terms of practice, there is only one knob. But because D infinity and number of lambda in that case, two different knobs, can't we jointly optimize them in some way to make it faster, even than just letting it run for like 20 iterations?
No. So the question, if I understand correctly, is here I have one knob and here I have another knob. I've been thinking, and you're right, of this as the computational knob and this is the statistical knob. But maybe I can just now use both as statistical knobs and cross-validate both, okay? It turns out that this is always, at least theoretically, is always the best choice because statistically, they're going to have these two methods. If you go and do the statistical analysis, have the exact same properties. They don't do much better or worse. And this is basically the one where you pick lambda equal to 0 and you do the least number of potential iterations, okay? So at least in this simple case, the answer is that the question is legitimate and the answer is do this. So you don't need to do cross-validation then discover it. You can prove it a priori and go with it. Yes?
So this whole lecture talks very specifically about the case of linear regression.
Yes.
And I guess part of proof of why they're very similar is because of the form of the derivative of linear regression.
Yep.
Right?
Yep.
So how does this
Right.
How would we show that?
So let's say I'm trying not to answer the question answer is, so the question is everything we said is about least squares, okay? Everything. So how much of this carry on to other stuff? Okay, now one way to get past the question would be empirically, it does, okay? And before you go nuts and prove things for neural networks, you might want to check things for linear models, okay? And see if the same effect holds. And that's what we did here, and that's why we teach it, okay? Clearly, from a mathematical point of view, and I would say more generally from a scientific point of view, the question of proving that is actually all true for neural networks or more complicated norms and loss functions is completely legitimate, okay? So some things are easy. So I would say, let me tell you three, which is the last thing I wanted to say anyway. Let me give you 4 levels of generalization you can go through, okay? And what we know and what we don't. I would roughly say that least squares are a bunch of things that we don't know, okay? So let me go here, laundry list, the implicit regularization laundry list, okay? Well, it's not, the laundry list is not. That's like of open problems. It's nicer, right? Okay, one coordinate you can move on is the optimization coordinate, okay? Stick to least squares. We don't do right away what you want. But let's just say, let's stick to least squares. What we analyze is the dumbest algorithm on earth, right? Gradient descent batch. What about acceleration? What about stochastic gradient? What about mini-batch stochastic gradient with acceleration? What about tail averaging? What about weighted averaging? What about... Well, we know some and we don't know some, okay? So, again, acceleration, okay? Batching, mini-batching, SGD. Of course, we have studied them before, but we have studied to the purpose of minimizing the empirical objective. Now we want to ask what they do for the test error. And so the question is not quite the same. And for example, an obvious kind of potentially contradictory thing is acceleration good? Because in the face of converging to an overfitting solution, going there extremely fast might not seem a great idea, right? And we kind of know the answer to this. And it's basically that you just have stopped before, okay? If you have to stop, you can stop before. So it's actually acceleration is good for a slightly different reason, okay? But it's just to tell you that the first direction you can move on is other optimization techniques. And already for least squares, this is only partially done. For example, for SGD, the majority of studies study one pass stochastic gradient descent when the goal is expected risk. But the effect of multiple passes to test error is still only partially known. Loss functions. Here, and maybe we'll do it as an exercise, showing, at least in some regimes, that you go to the minimal norm solution is actually not so bad. Let me rewrite this 1 second, okay? Put lambda equal to 0 and do still linearly squares. So I put lambda equal to 0 and I do least squares. I get these. This L prime stands for subgradient or gradient of the loss. And I use the fact that this is a linear model to pull out this xi. Then you see, this means that if these converge, this is also in the linear span of my data. So if it does converge, it converges in the linear span. Okay? For certain loss function, for example, the loss function that are for regression, this gives you the answer. At least when you can interpolate, you go to the right place. Okay? For classification, it was proved last year. Okay? It was proved last year that for linear models, for logistic regression, maybe a year and a half ago, you actually converge to the minimal norm that is the max margin solution. Okay? So again, this will give you the feeling that seemingly relatively simple questions are yet to be fully understood. And the proof is not as simple as we would like to be, okay? So this says that for generic loss function, you cannot go to the same place, okay? Proving that you actually have this kind of behavior, that the whole path behave nicely, like we did here, we know for some and we don't know for some, okay? We have kind of results, but they're not so great. Another question is, are there norms or regularization? What I mean here is, we didn't discuss this at all, but what about I want to use another norm rather than the square norm? And that's also only partially studied. The intuition is that, and essentially the answer here is, do things like use Bregman divergence and mirror descent. Which intuitively are the way in which you explain to gradient descent that the right geometry is not the one of the Euclidean norm, but is another one. In the sense that you would like to converge not to just to any solution, but to a minimal, whatever norm I like solution. So you have to tell it to gradient descent. So what you do, in the first order derivation of gradient descent as a first order approximation to the objective, you put the right norm, okay? And you use Bregman divergence. I don't have the time to do this, but I'll add maybe one reference. But again, there are like 2 papers, okay, on this, and they're for linear systems, not even for learning. So there is a lot of work to be done here. And last but not least, my short notes for kernels or neural networks, okay? And roughly speaking, for kernels, whenever you can do least squares or linear models, you're good. So we are actually pretty good here. You know, it basically goes back to what I told you. For this, you wait for Tommy. I would say the fact that the phenomenon is at work is clear. And some basic result that show the foundation that this is the way in which you can go to get results is done. If you compare to the super fancy results you may get for linear least squares, then there is more stuff to be done. But in some sense, I think at this point, the evidence that this is really a principle that holds across a whole variety of optimization technique, loss function, norms, and models is clear. And if you think that people have been working on this for 30 years, then it's not so surprising there is work to be done. I'm a bit late. Let me just add one more word, which is, you know, in machine learning, there is this fantastic job that you tend to not read anything that was done before and come up with a new name, and there is no exception here, okay? So presumably, we might want to call this something around gradient descent learning or gradient descent iteration stopping, whatever. So classically, this has been called the Landweber iteration, so it's a name you find, you know, because it was done in 1955 from the perspective of regularization, going to the pseudo-norm and so on. But then, of course, in machine learning or statistics, we have a better name, which is L2 boosting, okay? This name, implicit bias less regularization, is the 2019 name. You can also find the 1954 name, which is iterative regularization. And there are books about it. And the books are like, 30 years old. They don't quite look at the problem we like. They maybe look at deterministic problems, deterministic noise. So I'm not just trying to say here that everything is done, far from it. But I'm just saying the problem or the idea has origin in a lot of previous literature, okay? Okay, so I think this is pretty much it. The slides are going to contain a little bit more. You can look it up and we can discuss.